Hello everybody and welcome to chapter 4.4 of trigonometry. Today we'll be dealing with a completely new concept revolving around compound angle formulas. So we only are covering technically two topics. One of them is how to derive the formulas and then how to apply those formulas. So let's get started. So when it comes to deriving the formulas, it's actually a little bit complicated at first, but I promise you it won't be difficult after. The way you find the formulas is through the unit circle. Everything we do in the trigonometry unit will revolve around the unit circle in some form. However, don't worry, I will explain it to you. But with that, compound angle formulas are the formulas that will help you find the values of compound angle expressions. Those are the expressions where you have more than one angle. So for example, we've been dealing only with sine of theta, for example. We were never talking about an angle of like theta plus theta 2, for example. Or like theta plus beta, you know? But this is where these formulas come in to help you out. Again, I will show you how to derive them in a couple of seconds. So let's get started. I made the following unit circle here with a small angle of B and a larger angle of A. So if we want to find what the angle of A minus B would look like, it's actually quite simple. Since A is already covering B, the whole angle that we're looking at is just the angle over here. This one. This is A minus B. So our triangle now is the following. It would be this side, and this side. So, how can we figure out what its coordinates are? Well, it's rather simple. This one we've been dealing with forever, and we have learned that this would be our x and y, right? Which is the same as cosine of b, right? And then sine of b. What would be our angle over here? So let's think about that. Well, again, this is rather simple. Now we're just talking about this angle in reference to A. Therefore, our x and y values would now be cosine of A and then sine of A. So now we got our 2 points. This one, and the origin, which is 0, 0. Now that we know the coordinates, we actually get into some fun parts, which would include some of the concepts you learned back in grade 11. The first one being the cosine law. If you don't remember what the cosine law was, it's actually pretty simple. It was c squared is equals to a squared plus b squared minus 2ab cosine of our angle, so theta. So with that, we could actually start substituting in values. What we know for sure is that we could substitute 1 for the lengths of the arms, right? Because that's the radius. So c squared is equals to 1 squared plus 1 squared minus 2, 1 times 1. And our angle here is cosine of a minus b. From here, we could also find another way to define c. If you remember, let's label this first. Our second way could actually be using the length formula. We're given both of the coordinates, so it should be rather easy. The length formula was defined as c squared is equals to the difference of x1 minus x2 squared plus y1 minus y2 squared. So now let's substitute the values that we know. So c squared is equals to cos A minus cos B squared plus sine A minus sine B squared. Okay, now we have two of the same constants, right? So we could rewrite them in terms of one another. So at first what I would do is simplify this over here. So this is c squared is equals to 1 plus 1 minus 2 cos A minus B, which, sorry, I don't have enough space to write it fully. Cos is equals to 2 minus 2 cos A minus B. Okay. Now let's equate this and this. So what we get, I'm gonna start, that's personally how I like to put our final steps, or my final steps. So 2 minus 2 cos A minus B is equals to cos A minus cos B squared plus sine A minus sine B squared. From here, we could actually start expanding this side over here. So what we get is 2 minus 2 cos A minus B is equals to cos squared A minus 2 cos A cos B plus cos B squared, cos B squared plus sine squared A minus 2 sine A sine B plus sine squared B. From here, if you had a keen eye, you might have noticed that we have cos squared and sine squared, cos B squared and sine B squared, and if you add a cos squared and sine squared, you get 1. So I'd like to isolate those 4 values. So let's move everything else to the other side. So we get 2 minus 2 cos A minus B plus 2 cos A cos B minus, nope, still plus 2 sine A sine B is equals to cos squared A plus sine squared A plus cos squared B, we're running out of space, that's not good, plus sine squared B. Okay, as I said, those last values are equal to 1. So what we get on this side is actually 2 cos A cos B. Again, this is just a lot of writing, but don't worry, it'll get simplified sooner or later, is equals to 1 plus 1. So now we could bring this value to the other side. We know that this is 2, and we have 2 on this side, so we actually just canceled them out, right? So we get negative 2 cos A minus B plus 2 cos A cos B plus 2 sine A sine B is equals to 0. Now I divide everything by 2, so, or you could do negative 2 for example, so we get cos A minus B is minus cos A cos B minus sine A sine B is equals to 0. Now our last step is to just isolate cos A minus B, and we just move these two values to the other side, and what we get is cos A cos B plus sine A sine B. So does this seem very similar to what we found? It should be, because it's the exact same thing. So using this wonderful diagram, we have found out that cos A minus B is equals to cos A cos B plus sine A plus times sine B. Now that we found those out, we could find all the other formulas, as again, cos and sine are closely related, and also addition and subtraction are very similar too. So for example, let's look at the next thing. I'll write it over here because they're not as long anymore. So our other formula is cos of A plus B, and that is actually equals to cos A cos B minus sine A sine B. So as you can see, the only difference here is now instead of a plus like we had before, we have a minus. So the signs just switch. The way we could find this out is actually rather simple. So let's use our cos A minus B formula we just found out. Well, we could write A plus B as the following. We could write it as A minus negative B. So what that would mean is that we have cos A, cos of negative B, minus sine A of sine of negative B. with that, we could actually just talk about negative angles. So let's think about it. If we're talking about negative angle, which would be over here, this is our new b value. Using the cast rule, we know that if it is in the fourth quadrant, it's a cosine. That actually is still a positive value. So cos of negative b is actually the same as cos of b. However, sine of negative b is negative, so we actually get a negative removed from here. And a negative times a negative is a positive, so we get sine A and sine B. So again, that just proves that cos of A plus B is equal to the following. Now we could get into our other formulas, which is concluding or revolving around sine. So for example, let's first do sine of A plus B. Sine of A plus B is pretty similar. What it equals to is sine of A cos of B plus cos of A sine of B. So they just swap. You see we had sine of A, then cos of A, cos of B, and sine of B. Also the sign stays the same, so it could help you remember it easier. So let's really talk about what this is. We need to remember the identities from last class. The identity was that sine of x is equals to cos of pi over 2 minus x. And that cos of x is equals to sine pi over 2 minus x. So from these identities, we could rewrite what sine of A plus B equals to. Sine of A plus B, let's write that, sine of A plus B is the same as cos of pi over 2 minus A plus B, which we could rewrite further. So this actually equals to cos, and then let's move A, or take out the brackets, and we would get pi over 2 minus A minus B. You could put brackets around this, because now what we're dealing with is this formula once again. So we're using the cosine formula for compound angles. So let's do that. Cos, do you want to do it over here? Let's do it over here. Cos of pi over 2 minus A minus B is equals to cos of pi over 2 minus A cos of B plus sine of pi over 2 minus A, and then sine of B. Okay, so what do we know from here? These are again the formulas we learned yesterday, or the identities we learned yesterday. We know that this is actually equals to sine of A, so cos sine A cos of B, and sine of pi over 2 minus A is the same as cos x, or cos of A, so we get plus sine of A, or sorry, cos of A sine of B. Again, if you look at the formulas, they are the same. Therefore, we have found our other formula. Lastly, we have the subtraction formula for sine. Oh, so just give me a second. I want to extend this. There you go. Our last formula is the subtraction formula for sine. So sine of A minus B is equals to sine of A cos of B minus cos of A sine of B. Similarly, we are just gonna substitute or rewrite this as sine of A minus negative B, which then we're just inserting a negative B for the B values. So sine of A cos of negative B minus cos of A sine of negative B. Again, using the cast rule, we find out that this is still the same as cos of b, and then a negative value forms when we take sine of negative b, so this becomes a plus, so you get cos a sine of b. Again, these are the same formulas. Sorry, I noticed a little mistake that I made. Over here, it should have been a plus, and I didn't make a plus, so let's redo that. So this should be a minus, and over here I should have been sine plus. Sorry, yeah, that was a very dumb mistake of me. But again, the principle stays the same. With these, we have found 4 of our main formulas. You can also find the tan versions of these, but when I was studying them, we didn't have to find them all, because actually the tan formula is a little bit tricky to figure out, and for that reason we actually never did it. So if your teacher actually shows you how to do it, try your best to memorize it. I'll also show you what it equals to, but I'm not going to show you how to derive it. Now that you know how to derive the formulas, I have written them down for you so that it's easier for you to remember. So here are our cosine formulas. So cos of a minus b is equals to cos of a times cos of b plus sine of a times sine of b. So all you essentially have to remember is just the visual format. So we have 2 coses and 2 sines together, and then you flip the sign. So using that, when we have cos of a plus b, we should have 2 coses, so cos of a and cos of b, then we flip the sign, so it should be a negative, and then 2 sines, so sine of a and sine of b, which is exactly what the formula is. When it comes to sine, it's almost identical, except again, we're just going to be dealing with the format. Remember that it is now alternating, so you have sine a, sine a, cos b, cos a, sine b. So you have a sine, a cos and a sine. The sine stays the same this time. So all you gotta remember is to flip the sine and cosine. Again, just an easy check if you did it right is that if you have one sine with an a and one sine with a b, and then you fill in the blanks. The same thing works for sine of a plus b. Again, the sign stays the same, so it's a plus, and then everything else is identical. Next, we're talking about tangent. Tangent, as I said in the video that you just watched, or the part you just watched, it is not usually derived. There is an extended question in the textbook that makes you derive it, which is not that difficult. All you're doing is applying the identity of tan of theta is equals to sine of theta divided by cos of theta, and with that you could substitute it into the cosine and sine compound angle formulas and solve from there. But you'll still have to know what the formula is, even if you don't know how to derive it. That's why I've written it down here. So tan of a minus b is equals to tan of a minus tan of b, all divided by 1 plus tan a times tan of b. When it comes to the opposite version, so tan of a plus b, you're just flipping the signs. So if you had a plus, top has to have a plus and the bottom has a minus. If you had a negative, so the top has a negative and then the bottom has a positive. Again, you have to know all these formulas for when it comes to this chapter. You need to apply them when it comes to trigonometric identities, which we'll be doing next chapter. So make sure you memorize these. With that out the way, we can now start actually applying the formulas. Again, you could use the compound angle formulas to evaluate trigonometric ratios for values other than the multiples of special angles. So for example, let's do the first question. This question asks us to find the exact value of the following expression. Sine of 2 pi over 13 cos of 7 pi over 39 plus cos of 2 pi divided by 13 and sine of 7 pi divided by 39. This is a really long boy, and you might be very confused on how to do it. Well, the first tip would be to identify the type of compound formula we're dealing with. So we have a sine and a cosine. Immediately, that should tell us we're dealing with a sine formula. Now, since we have a plus in the middle, that means the original function or the original formula also had a plus. So the only option we have is the compound angle formula for sine of a plus b. So with that in mind, we could find our a values, which would be the first and second bracket. So a is equals to 2 pi over 13 and b is equals to 7 pi over 39. So now I just plug these values into our equation or our expression. So we get sine of 2 pi over 13 plus 7 pi over 39. Then I've simply added the fractions. So I made the denominator the same by finding the lowest common denominator, which you should remember from our rational chapter. Now, with these denominators being the same, we could add the numerator. So we get 6 pi plus 7 pi, which is equals to 13 pi. Now, we just need to reduce the fraction. Since 13 and 39 have the same factor of 13, we could just remove it. So we actually get that this is equals to sine of pi over 3. Again, you should remember that pi over 3 is a special angle. So now that we're dealing with a special angle, you could simply just draw a little triangle to find out what it equals to, or by now you might have already memorized that it equals to square root of 3 over 2. So we found out that that extremely long expression is simply equals to the square root of 3 over 2. That's the beauty of applying the compound angle formulas. Now let's move on to example 2. Find the exact value for the following, and that is cos of 5 pi over 12. So in the previous chapter, we realized that we could rewrite these, right? Like 5 pi over 12. How can we express it? Well, in here, we could express it as the sum of two angles. I know, isn't that convenient? So our two angles could be 3 pi over 12 plus 2 pi over 12. With that, we have found two special angles, right? Because we could reduce 3 pi over 12 to pi over 4, and 2 pi over 12 can be reduced to pi over 6. Now, we have to apply the compound angle formula for cosine, and with addition. So that is this formula. We have cos of A times cos of B minus sine of A times sine of B. So we've written it here. Now, you might get a little bit confused, but not to worry. All you have to do now is simply plug in the correct values for each trigonometric ratio. So again, these are all special angles, so you could create your two right angle triangles where one has an angle of pi over 4 and the other one has an angle of pi over 6 and pi over 3. And from there you could find out that cos of pi over 4 is 1 over square root of 2. Or you could again just remember it. You also, from there, what you do once you find all of them is you multiply the two things that are right beside each other, which is rather simple. Just multiply the numerators together and multiply the denominators together. So doing that gets us the following: square root of 3 divided by 2 square root of 2, and then minus 1 times 1 is 1, and 2 times square root of 2 and square root of 2. From here, we could simplify. We could subtract the the values from one another, since we have the same denominator. So we could get square root of 3 minus 1 on the numerator and 2 square root of 2 on the denominator. Now, you might forget this last part, but I assure you it is extremely important, and teachers are extremely picky about it. You need to rationalize the denominator. The way to do this is to just find the radical. So in our example, we got the square root of 2. So just multiply the whole expression by the square root of 2. When you do that, you're multiplying the denominator by square root of 2, which would cancel out the square root, and then multiplying the numerator by square root of 2 would mean you're actually collectively multiplying the whole expression by 1. Because remember, square root of 2 or square root of 2 is just 1. So with that, what our final answer would be square root of 2 times square root of 3 minus 1, all divided by 4. I don't recall my teachers ever asking me to go further than this and then like expanding it, so then I get 2 radicals multiplied by each other. But again, listen to what your teacher says. Now, this is our last example for today, but tomorrow we're gonna get a bonus unit where we're gonna do more of these questions. It's actually a lot of fun. So, our example 3 asks us to evaluate sine of a minus b, where a and b are in the second quadrant. However, we also know that where sine of a is equals to 4 over 9 and sine of b is equals to 5 over 13. Okay, so we know that we're dealing with sine of a minus b. So immediately just write down the formula so you don't forget it. Sine of a minus b is equals to sine a times cos b minus cos a sine b. Now, from here, we already know 2 of the values. We know what sine a is and sine b is, so we plug those in. So we get 4 over 9 times cos b minus cos a times 5 over 13. Sorry about that. With this, you might get a little bit confused, but that's why I made this little help box over here. I don't know what else to call it. So from here, what we need to remember is that sine of x refers to the relationship between the opposite side and the hypotenuse, right? Since we know that sine of a is equals to 4 over 9, we know that the opposite side is equals to 4 and the hypotenuse is equals to 9. Using the Pythagorean theorem, we could actually find our last side, which would be the adjacent side. So the way we find it is, of course, just applying the formula of a squared is equals to b squared plus c squared. So in our case, I just rewrote it as the adjacent side is equals to the square root of our hypotenuse minus our opposite side, which would lead us to have the adjacent side equal to square root of 65. Now, since we know the adjacent side, we could now write what the trigonometric ratio equals to. So cos of a is equals to the adjacent side, which is square root of 65, divided by the hypotenuse, which is 9. Therefore, cos of a is equals to the square root of 65 over 9. However, this is extremely important that you notice this. In our question, it said that we're in quadrant 2. Using the cast rule, we know that sine of theta will be positive, but cosine of theta will always be negative. Hence, we have to add a negative to this value for it to hold true in the second quadrant. Now, we use the exact same procedure to find cos of b, and I made cos of b a little bit simpler to find since you're not going to be dealing with a radical. Once you do that procedure, you'll find out that the value you were searching for is negative 12 over 13. From here, it's again pretty straightforward. We just multiply the two fractions together. So again, numerator times numerator, denominator times denominator, and we get these two expressions. Next, we just add the 2. So we get negative 48 plus 5 square root of 65 divided by 117. Then I like to personally remove the negative so I could get like a full negative fraction, because for somebody, like, you might not understand whether or not this would be a positive or negative value because you're not quite sure what square root of 65 is. This just makes your life a little bit more easier and easier for the reader. So overall, I just removed the negative 1, so we're left with negative 48 minus 5 square root of 65 all over 117. With that said, that was our whole lesson for today. As you could see, it was a lot of formula work. There wasn't any graphing, there wasn't anything really to do with using the unit circle to explain things, except for when you're deriving the formulas. I'd say it's really, really important for you to remember how to derive these, because I'm pretty sure it was a communication question on one of my tests. So practice that in your own time. Other than that, here's the homework for today. I've assigned one 1AC, 2BD, 3AD, 5A, 6B, 8, and 9. I made sure that all of these questions follow the 3 examples we've done today. And for that reason, I again will not be going over how to do them, but I will show you what those questions look like. So let's take a quick look at them. So for 1, we have sine and cosine, so we know with a plus, so we're applying the compound angle formula for sine of A plus B. Here it's a negative, so sine A, sorry, for this one we have cos and cos again, which means it's a cosine formula, and with the negative, remember this is the opposite of the angle used, or the sign used in the formula, so that particular one would actually be cos of A plus B. Then for 2, we have the same exact type of questions, just now we're dealing with things that are not in the same quadrant or not in the same simple format that we're used to, but again, I showed you how to deal with these kind of numbers in the first example we've done. Then 3, we've already gone over, so that's not a big deal. The rest of them over here, we've also gone through. 8 and 9 are very similar to the last example we did, except here we're actually defined for sine of x and cos of y. So again, you just use the same strategy we did to find either our adjacent or our opposite side. And once you find those two, it's really simple. You just plug in those values, right? So when it's asking us to find the value for cos of x, that's the second step or the third step we did in our example. And then it's just asking you to plug in those values. So with that being said, thank you for listening to today's lesson. I understand it might have been a little bit difficult or surprising to you, the new content that we've learned, but I will be making another lesson that is actually not in your textbook on double angles. Double angles are just another formula you can derive from using the compound angle formula, and for that reason, personally in my own school, we've been using it for a lot of trig identities because it makes your life a whole lot easier. With that being said, I hope you had a lot of fun listening and again have learned a lot. After the double angle formula, we only have one chapter left or subchapter of chapter 4, and with that, we'll be halfway done the course. So I hope you're excited for that. Otherwise, thank you for listening and have a great day.